Hi everyone, we'll present our work for ICCV 2025, exploring multimodal diffusion transformers for enhanced prompt-based image editing. Recently, we've seen two major shifts in diffusion community. Formulation-wise, DDPM-style noise prediction has changed to conditional flow matching paradigm. Also, diffusion model architectures have changed from UNets to transformers. Many of the state-of-the-art models, like SD3 and Flux, are based on this multimodal diffusion transformer, or MMDIT. However, due to MMDIT's fundamentally different architecture and mechanism compared to UNets, many of its inner workings are yet to be explored. In this paper, we start with two questions. How can we extend existing unit-based findings to these recent architectures? And can excellent generative capability of these models be transferred to editing capability? We present some valuable architectural insights about MMDIT and present a robust prompt-based image editing method. Conventional UNet architecture uses separate self-attention for the image's spatial structure and cross-attention for text guidance. The key is the unidirectional information flow. Text affects the image, but not the other way around. In contrast, MMDIT uses a unified full attention mechanism where image and text tokens are processed together in a dual branch structure. This creates a much richer bidirectional relationship between them. Some variants include compute-efficient single-branch blocks in Flux or explicit image self-attention in SD 3.5. These models also tend to be larger, benefiting from scalability of transformer architecture. Table summarizes architectures with their inference times with and without SDPA attention kernel. The core mechanism of MMDIT is a full attention mechanism on a single concatenated image and text tokens. Here we bring SD3's dimension as an example. Query, key, and value matrices are concatenated and full attention operation is performed. The resulting attention map can be divided into four distinct subblocks, which are I to I, image to image, T to I, text to image, and I to T, image to text, and T to T, text to text. We omit softmax operation, which is done row-wise for convenience. I to I block resembles self-attention in UNets, capturing the spatial layout and geometry of the image. T to I and I to T blocks are where text and image modalities are fused. These blocks are important since we can derive each text component's effect in image, potentially using it for obtaining attention masks. Amongst these two, we find T to I block to provide cleaner attention maps than I to T block. In I to T blocks, rows correspond to image tokens, and there is an inherent competition as their attention weights must sum to 1, diluting the signals during softmax. In contrast, T to I's structure allows multiple image regions to retain high attention values simultaneously. Replacing different subblocks has a varying impact, with I to I being critical for preserving the source structure. However, as MMDIT models get larger, we observed noisier attention maps. This observation aligns with recent paper, Vision Transformers Need Registers, which reported similar issues in scaling VITs. This noise can introduce artifacts during editing, especially for precise local blending where we perform binary thresholding on attention maps. We propose a two-part solution to obtain clean attention maps. First, we systematically identify the top 5 cleanest transformer blocks for each model by comparing their attention maps to ground truth masks from grounded SAM2. We use BCE, soft MIOU, and MSE to measure each block's similarity to GT mask. Note that the top 5 blocks are not prompt-specific, as they are selected based on diverse text queries from 100 party prompts. Second, we apply a simple Gaussian smoothing. Using these top 5 smoothed blocks gives us much cleaner and localized attention maps. Here's an example showing effectiveness of block selection and Gaussian smoothing. We have 3 key considerations for editing method, which are reasons why we can't directly change attention maps as before. 1. With larger models, we need to use SDPA kernel or flash attention. When we operate at attention map, they cannot be utilized, requiring token-level operations. 2. Simply changing all target query key matrices with source query key yields text misalignment issue with value matrix, which we show later. 3. We need MMDIT tailored method to obtain high-quality binary mask for precise local blending. Our solution is to replace only target branches image tokens with source image tokens and use selective attention map calculation based on our previous experiments. Our approach is fast, avoids text misalignment, and allows for very precise local blending. Now let's go through our pipeline. We run two parallel branches in the model, a source branch with the original prompt and a target branch with the edited prompt. Now let's dive into our attention manipulation mechanism inside the ith MMDIT block at the teeth time step. Here, the source branch just does the plain old attention with SDPA kernel. However, for the target branch, instead of letting it to generate its own image structure, we replace its image query and key projections with their counterpart from the source branch. This is the core of our method. It preserves the structure and identity of the original image. Then we do attention with SDPA kernel. Changing image tokens ensure that I2I subblock part of the two attention maps are identical. You can see that the I2T and T2I blocks are also being influenced by this replacement, but our experiment shows that results do not differ much with the one where we replace only I2I block, which disables SDPA kernel usage and leads to 3 times slower inference. Changing only image tokens also ensure attention maps text tokens align properly with value matrices text tokens. So far, we've seen case without local blending. This alone works well for global edits. For local edits, we can optionally add a blending step to better preserve the original contents. Local blending is the method of mixing the image latent of two branches using the binary mask derived from thresholding attention maps. In top 5 clean blocks mentioned earlier, we store attention maps T2I blocks with Gaussian smoothing to obtain binary masks for local blending. At each sampling step, we preserve target tokens in regions that are strongly associated with our editing words based on the attention threshold and replace tokens in weakly associated regions with those from the source branch. Here we compare full query and key replacement with image token replacement. Replacing full projections yield suboptimal results with unwanted background changes or artifacts. Our approach of modifying only image tokens avoids misalignment and can handle arbitrarily different prompt pairs. Our image token replacement approach produces nearly identical results to eye-to-eye attention map replacement, but is more computationally efficient. By adjusting local blending threshold, you can also modify the edit granularity. There are a few key hyperparameters in our approach: which time steps to replace projections, how many blocks to modify, and the local blending configuration including steps and thresholds. Although all of these can be optimized, we find that most edits work well by just tuning the local blending threshold while keeping everything else fixed. For the full algorithm and detailed parameter analysis, please check out our paper. We conduct user study and quantitative evaluation using 2 simple baselines. They reveal that our method uniquely balances strong target alignment with content preservation. We provide additional results in the paper, including quantitative benchmarks on PyBench and qualitative comparisons with other notable baselines. Please refer to the paper for details. In conclusion, our work provides the first architectural analysis of multimodal diffusion transformer with several insights. We've proposed an efficient, training-free method that achieves state-of-the-art results for both local and global edits on the newest generation of models. There are a few limitations. Since we modify spatial layout through eye-to-eye components, non-rigid edits remain challenging, and some hyperparameter tuning is still needed. We leave these as future work. Thank you for listening.